So today we're going to be talking about bridging the cloud divide. So this was inspired by the theme of bridging the divide for ESIP this year. And this is going to be broken up into two sessions. This first session is focused on technological advancement. So basically, the cloud computing cluster is and continues to be a place where we like to highlight what technologies are being developed to facilitate science adoption or doing your science on the cloud. So we're going to be hearing from five different speakers, as well as Miguel is going to be giving an update, is going to be giving a report out from the Chunk Manifest Standards Development. So we're going to start out with hearing from Jarrett Kiefer, who is going to be providing a little bit of background on how you store data on the cloud in order to access it in a cloud native manner. So he's going to be talking about chunks, as well as a new way of accessing that data, that a new type of protocol that is an exciting idea. And then we're going to be talking about how to structure and store data on the cloud. And we're going to hear from Max Jones and Joe Kennedy on a worst practices data cube guide, and also cloud optimized NISAR. And then we're going to be talking about how to integrate storage. So once we've stored data on the cloud, how do we deliver it how do we deliver it to users, right? So what are the APIs and libraries that are being used to actually leverage this data as it's been, optimally stored on the cloud in these new standards? And then finally, those new standards are something that are obviously continuously being evolving and being developed. Hopefully they reach stability eventually, but right now a lot of them are still being developed. And so one of them is this one sort of standard that's being developed and has its own iteration in many different formats is Chunk Manifest. So there was a really great session led yesterday by James Gallagher and another of other facilitators in this meeting. And so we in that meeting discussed, what is a chunk manifest and what is the standard for chunk manifests. So really excited to hear that report out and continue the work on that, probably as part of the cloud computing cluster. So with that, I'm going to stop sharing and I'm going to pass it off to our first speaker. Before I do that, also, if you have questions during people's presentations, feel free to throw them in the chat and we can ask them either if they have time within their allotted 15 minutes, we can ask those questions within that 15-minute window to that specific speaker. If we need to move on to the next speaker, we will hopefully have a few minutes at the end of all the presentations to take any last-minute questions or follow up on those questions that you've put in the chat. Yeah, and then if the speaker has the opportunity, obviously they can answer it in the chat themselves. Any questions or last minute reminders, Aaron, you think I should mention before I start the presentations?
Nothing here.
Okay, great. I'm going to stop sharing and pass it to our first speaker, Jarrett.
All right, let's see here. Okay. I probably won't have any time left to answer questions, but I will jump into the chat if there are any. And I'm always available on Slack or wherever else. So hello, everyone. I'm a geospatial software engineer at Element 84. And in my role, I focus less on data itself and using data and more on the infrastructure around the data, like process orchestration, indexing, and search systems. And my notes are obstructed. Okay. And how data is made available to end users. Finding opportunities to increase efficiency in data access fits right in with all of that. And that's a bit of what I'm going to be talking about today as we look at redefining cloud native with the Coalesce chunk retrieval protocol. I'm going to start all of this off with a few fragmented ideas, but hopefully there's a thread here that will pull all of this together. Before we get any further, though, maybe we need a starting definition for cloud native before we consider redefining it. So what is cloud native, specifically as it pertains to geospatial? If you've ever seen Idiocracy and know this scene, I feel like defining cloud native geo kind of goes like this. Cloud Native Geo is all about using cloud optimized data formats to make data access more efficient. But why are cloud optimized data formats more efficient? Because they're in the cloud. What good is the cloud? Well, we can do things cloud natively at scale, and on it goes. Of course, I'm being a bit facetious here. Please allow me to continue to do so for another moment. The best I can figure, when I break all of this down, Cloud Native Geo means using S3 or any of your other preferred object storage solution to host data because we're lazy and we don't want to run infrastructure ourselves. And then we do a bunch of things with special file formats and client-side tooling to try to work around the high latency that S3 introduces, and we call the result Cloud Native. Now, to be sincere, please don't get me wrong here. Doing things this cloud native way means we can realize scales of data processing and storage that have previously been out of reach or limited to the very largest HPC clusters. Being lazy and using cloud infrastructure means we can focus our limited resources on innovation that adds value to our efforts, not building and running unremarkable services. This is a good thing. But I have to wonder, is this really the best solution using S3? Object storage is a great technology, but it was designed to serve web assets, files, not massive multidimensional data sets. Is this really the optimal solution, or have we merely arrived at a local maximum? I start to wonder if it's the latter, and I think we should be exploring what cloud native could come to mean as technology continues its march forward to something beyond object storage. Let me try to explain why. To do so, I need to talk about chunking. So chunking relates to the topic of linearization. All data represented within a computer must be a one-dimensional string of bytes. So when we have n-dimensional data, like arrays or tables, we need a way to project those n dimensions down to 1 in order to represent that data within the computer. Chunking comes into play in linearization because we can use chunking as a layer within the linearization process to further increase spatial locality. We need to care about chunking because chunking is a tool in data formats that is common to all types of data, not just rasters, and is a key part of cloud optimized formats. It is also super important for another reason. Chunks are a unit of compression, and thus become the most granular unit of access we have to read from and write to n-dimensional datasets. I vibe coded this cool tool called ViChunk to help me play around with and understand chunking and linearization and their effects on read efficiency. I'm not going to do this topic justice here, but go play with ViChunk if you want to learn more about this. As well, my coworker Julia Signell and I wrote a couple blogs on chunking. You can read those too if you want. The takeaway from this for now is it turns out that chunking is super useful and absolutely necessary, but appeared to us as something tyrannical. Chunking misaligned with an access pattern can cause significant data access inefficiencies. Big chunks risk read amplification and having to download way more data than is actually needed. Small chunks negate that risk. Like, well and truly, small chunks are the solution to read amplification. The problem is, today, with object storage, small chunks increase the number of read requests required to fetch data. Network latency on each request at scale can be crippling. Even parallelism, which is a massive help here, has its limits. So what can we do? Let's talk about object storage. Object storage is kind of like a file system. So a file system here, we can use a file system to map file names to data in those files stored in a backing block device. So all blocks containing data for a given file can be looked up based on that file's name. Object stores map object keys, file names, not just to data in a single block device, but to potentially massive distributed block store, perhaps with millions of block devices backing it. Object data is split up and duplicated across many of these block devices, so data can be read for a single object from many places in parallel, and the system is able to realize a level of performance greater than any single one of its parts. Let's consider a cog in our object store here. Now, when we read a cog, we don't request all the bytes of the cog. Instead, we read the cog chunk by chunk as needed. Chunk by chunk. Did I say bytes? No, we don't really even care about bytes, do we? We care about the logical array that this cog represents. What if instead of making client-side tooling go through this linear object-based interface, we had something else, multidimensional? Maybe we call it a chunk store. Now, I just mentioned client-side tooling and what it does to read data from a cog and object storage, perhaps we should walk through that process in a little more detail so we're all on the same page. We'll use a simple example of an array chunked 4 by 3 here, which we know is linearized some way into an object. Let's say we want to request this highlighted region in the array. So first step, we have to fetch the metadata for our data set. This is an HTTP range request itself. Once we have that metadata, which includes the chunk layout in the object, we can proceed to step 2, which is to linearize our query. Logically, our query is one slice across 2 dimensions. But just as we had to linearize our multi-dimensional array for storage, so too do we need to linearize our slice. If in this simple example, we see that we end up with 2 one-dimensional slices within the linearized bytes of our array. We then make separate GET requests for each of those ranges. This is why we see request count go up when we make chunks smaller, because we end up having to request even more non-contiguous chunk byte ranges. I think considering how data storage differs with ZAR is an interesting contrast to this. If we look at our object store example again, but convert our cog to ZAR, we see we have a separate object for each of the array's chunks. Note 2 major differences with this. One, storing our chunks in individual objects means we can't coalesce reads for chunks with contiguous byte ranges, which is not great. But 2, notice we don't have to care about bytes anymore. A client can simply request chunks in their entirety, decoupling client requests from bytes. So what about this chunk store idea? The real issue with object stores comes from the imposition of the object model on multidimensional data access. That is, I think objects erroneously impose a linear byte-spaced interface for multidimensional data. So I think it's worth asking, do we even need objects for data access? Can we take another step beyond ZAR and make it so clients don't even need to consider chunks to request either? It shouldn't matter how the chunks are arranged within objects in the block store. We can ditch the object-based API when accessing multidimensional data sets if we maintain the mapping of dataset dimensions to chunk bytes in the API. That mapping, that index of dimensions to chunks to bytes that the client builds up today, we can just move that to the server side, and clients can then request any slice they want, for which we can resolve the appropriate chunks in parallel from the backing store. And if we map dataset dimensions to chunks server side, we can make chunks smaller without increasing our request count from the client. Now, the title of this talk mentions the Coalesce Chunk Retrieval Protocol, or CCRP for short. CCRP is my proposal for what a chunk store interface could potentially look like. Note right now, this is just an API spec. I published a rough draft of it at ccrp.dev. And this spec is intended to be a starting point for discussion. Pieces like some of the examples are LLM generated and do need heavy revision. But at a high level, I think the foundational pieces are all here. And all of this is open source, so anyone can contribute to this. Go open pull requests, issues, discussions, whatever. It's all on GitHub there. So the extent of the API as it's currently proposed looks like this. The main point here is that users can list all available data sets, then fetch the metadata for a given data set to find what they need to make requests for data. Head requests can be used to plan a query, and HTTP range support would allow using parallel download workers for large downloads or for resuming failed downloads. Here's an example of a request. We don't care about bytes here. We don't even care about chunks. We simply make a request via a slice within our dataset dimensions. The big difference here is that CCRP is not a compute engine. It's just a byte broker. It does coordinate to chunk resolution to resolve what all chunks are touched by a user's query and returns those chunks as is. I like to think of this like predicate pushed down in an API. Contrast this to something like OpenDAP or coverage services where the API is not just fetching and forwarding bytes, but transforming them potentially. And that's expensive, something CCRP explicitly avoids. Another point of CCRP, this idea isn't strictly relevant to array data. There's a realization here that array and tabular data structures aren't really that different, at least not conceptually. They're both representations of a hypercubic space of coordinate and data variable dimensions from which we want to slice regions. So a key goal of CCRP is that it can be an interface that facilitates efficient access to chunks in any chunked data format. Here's what the metadata for a data set might look like. This is really just a minimal object wrapping the native metadata format right now, but allows for extensibility in the future. Or at least this is what I had been envisioning initially. Though, as I've dug more into this over the last few months, particularly diving deeply into the Parquet data format, I've realized a bit of naivete here on my part. So my thinking has changed a bit, which leads me into what's next. Things are continually evolving with this idea, so this is by no means a solid roadmap, but here it goes. CCRP might not actually be the best place to start. I've realized my bias coming from the array side and my familiarity with raster formats. Parquet, as I mentioned, has uncovered unexpected complexities. Conceptually, CCRP remains, but the problem becomes one of metadata. How can we have a chunk API and provide metadata for datasets and chunks in a consistent way across both Zar and Parquet? I thought this would be easy, and I wanted to avoid having to define something new here, but it increasingly seems like a unified metadata representation is inevitable. And it's interesting to hear I'm not the only one necessarily talking about this. Maybe we're not using quite the same terms, but the Chunk Manifest working group that kicked off yesterday is quite encouraging to me, and I look forward to seeing how aligned that is with the ideas that I've got here. The metadata topic leads me down a rabbit hole. I start thinking about if Stack has something to teach us here, but I'm thinking bigger than just geospatial data. To give us a new cloud paradigm to rival S3, we cannot be thinking of something geospatial, if you will. We need a foundational technology that works equally well for non-spatial and non-temporal data. That's at the dataset level, however. We still need to talk about chunk metadata. Chunk metadata could include a lot, but generally must encapsulate two things. Statistics for chunks, so we know what we even want to read, and chunk encoding, how the data values are linearized and compressed, and any transformations therein. I think Zar provides a really compelling model here for expressing encoding pipelines, but codec incompatibility is a major concern for me. The ideas go on and on. I have an idea for like a virtual machine that could support an ecosystem of codecs that could conceivably be a form of a universal data encoding layer. But I'll cut all of this short to say I'd still love to see progress made on a high-level CRP proof of concept. I think working from both ends of this problem to meet in the middle is likely the right way to achieve success. But more than any of these ideas, what's next? Well, I could use your help. Right now, this is all just me pretty much on my own time. I really would like to see this be a community effort. So if you're interested in any kind of involvement, let me know. If you have resources to support this effort, please let's talk. And of course, maybe CCRP isn't even the right idea to redefine cloud native. But if so, that just means I need you all to help me come up with other new ideas. How would you redefine cloud native? What's your local maximum you'd like to see us move on from? I'm sure object storage is not the only assumed technology we should be discussing. Thank you.
That was awesome, Jarrett. Yeah, very, very inspiring. I think it's something that specifically the cloud computing cluster could hopefully help continue that conversation. Yeah, okay. So I think unless there's any quick questions, we should probably move on. Is there anybody that I don't know if that presentation spurs quick questions, but if there's anything that could be answered in a minute, happy to take it. Okay. Yeah, go ahead, Jarrett.
Like I said, if there are any questions in the chat, I'll jump in there, and I'm on the ESUP Slack now, so you can reach me there as well.
Yeah, yeah. No, I think some of your terminating questions were good ones for like continuing discussion beyond this session. So that's great. Yeah. So Max, you're up next.
Okay. Be sure. Wait, I don't want to show those. Sorry. Okay. Do you see just my slides?
Yep.
And I will drop here in the chat the kind of Zenodo link to my slides if anyone wants to or prefers to follow along on their own. Thank you, Amy, for organizing this session. And Jared, that was an amazing talk to kick us off. A hard one to follow for sure. I will be presenting today on the DataCube guide. My name's Max. I work at Development Seed, and I've organized this presentation into 4 different sections. Start out with some background on this guidebook. Give an overview of the bulk of the content, which is this DataCube worst practices section. Then quickly go over a vision for next steps and some entry points for getting involved. As a bit of background on the DataCube guidebook, Microsoft was building this Planetary Computer Pro, which I believe is still in preview mode, which is a unified geospatial data platform. And they recognized that in order to make the most out of this new product, people really needed guidance for how to work well with raster data cubes. And they also kind of appreciated that this DataCube guidance is applicable not only for their platform, but also across other disciplines and communities. And I appreciated that they also recognized that the content of this guidance would be best if built in an open and collaborative way. And so that gave rise to this DataCube guidebook. We partnered with them. My task was to build a DataCube best practices guide. I took a little bit of artistic license here and made a DataCube worst practices guidebook for a couple of reasons. The primary one is that the answer to what are DataCube best practices usually starts with "it depends," which causes a lot of eyes to glaze over. And in contrast to that, DataCube worst practices is a little bit more tangible, easier to define and digest. And steering people away from these DataCube worst practices will naturally lead them closer to DataCube best practices. And the second reason was very pragmatic in that this would be able to be built in the amount of time I had for the project, whereas a DataCube best practices guidebook would likely go on for many years and change rapidly. So let me go into a little bit about the content included in the DataCube worst practices section. I have divided this into 2 different portions. One is DataCube production gotchas, and the second is DataCube usage gotchas. This guidebook is deployed on the web at developmentseed.org/DataCube guide. This QR code will also take you there. And for the DataCube production gotchas, I've started by defining 6 common issues that I've seen with DataCubes, in particular available over object storage. The first is tiny data chunks, also tiny coordinate chunks, which in like X-rays based model is distinct from data chunks and can lead to kind of unique issues. Non-standardized metadata, massive data chunks, and dispersed metadata and bloated data types. And each one of these sections kind of mirrors each other in the structure. And I'll go over one of these in detail and then just encourage you to take a look at the guide for seeing about the other ones. So we start out with kind of the overview of what the issue is. In this slide, I have a very concise version of the reason for that. In the guidebook itself, you can have a lot more details about how this worst practice leads to consequences like inefficient compression, inefficient data loading, inefficient encoding and decoding workflows, as well as issues with parallel computing frameworks. And the majority of these also have demonstrations that show in practice what these different issues mean for data usage and storage. So I'll go over that for this example of tiny data chunks leading to poor performance. In the figure on the right, we have on the y-axis the storage size for, I think it's a 1 gigabyte multidimensional array, but the actual size doesn't matter. What matters is the relationship between these 2 bars, one which shows the storage size for a 25 megabyte chunk size and the other for 25 kilobyte chunk size. And you can see that the total compressed storage size for this tiny chunks is about twice that for a more reasonably sized 25 megabyte chunk size, which shows that if you have too small of chunks, your compression algorithm slows down loading and storing without much benefits to the storage size. Again, we kind of go into details for each of the issues that you might see due to these is defined as worst practices. The second is the performance of loading data, where the amount of time it takes to load data is the sum of the amount of time it takes to fetch it from object storage and decompress it. And we show on the y-axis the amount of time it takes to load this data for different access patterns, like loading the entire array, loading a spatial slice, loading a time series, or loading a random point. Again, grouped by chunk size, either 0.25 megabytes, 25 kilobytes on the left and 25 megabytes on the right. And for random access, like a spatial slice, a time series, or a time point, you don't see much difference. But if someone wants to load the entire array, which for a 1 gigabyte array isn't that unreasonable, having that take 10 seconds, almost 10 seconds versus just over 1 second is a pretty massive difference that will, I think, affect user satisfaction with this data product. And the last example here is the impact on the default Dask chunks when you just open this using Zar and Xarray. So we have on the top the HTML representation of the Dask chunks for the 25 kilobyte chunk size, and on the bottom, the HTML representation for a 25 megabyte chunk size. Just visually, you can see the massive amount of more chunks that Dask has to manage, where they typically map tasks on a chunk by chunk basis. Concretely, this is 37,000 chunks in this array versus 48. And for each of these issues, it is important to caveat it that these can be largely circumvented by user tuning. So you can configure how Dask chunks map to chunks on disk. You can coalesce adjacent reads to improve load performance for tiny chunks. The compression size is that's not something that a user can affect. But at the same time, most users don't tune their workflows. They don't configure the Dask chunking relative to the on-disk chunking. They don't configure coalescence using FSspec or obstore or whatever IO library. And so I think there is a lot of value in structuring the data on disk in a way that makes it so that users using default options have the best possible experience. So that was kind of the rundown for one of these DataCube production gotchas. Check out the guide, again, the QR code or the link here to look at the others. This is a starting point. I think we could add others, and it would be valuable to have this as a living guide rather than a one-time product. I also wanted to do a similar exercise showing one of the usage gotchas, which is using old libraries. Other ones we've kind of started with are using the default FSspec caching, using default GDAL configuration settings, or using the default Xarray combined arguments. This example of kind of a gotcha of not upgrading your software libraries is impactful because it can lead to slower code, missing bug fixes, and missing features. And I was really amazed by this figure from Jimmy Butler's AGU talk last December, where he shows the amount of time it takes to do his workflow. You can kind of ignore mostly the x-axis. It's just 15 different parallelizations over his atmospheric river analyses. But the important part is the difference between the blue bars, which are on the left of each group, and the orange bars, which are on the right, and showing that the upgrading Earth axis from 0.10 to 0.15.1 is an order of magnitude speed up with just a software upgrade impact. And this is something that I know you can see in Zar Python, you can see in different Xarray versions, and I imagine is pretty common across the software stack. And I do want to acknowledge that it takes a lot of sysadmin work to upgrade libraries in secure environments, and that this isn't a large task, but it is important to recognize the value you can get by putting that time in a lot of the case. Next steps. I think there's been I connecting to Doug's comment in the chat, we could put in a million different links for how many new topics there are around ZAR and DataCube visualization that have come out in just the last year. So here in the index is probably hard to say, so I'm going to kind of repeat it. We have a new section called DataCube visualization that I think would be really valuable to build out, likely in collaboration with NASA Data Project. In 2024, we did a ZAR visualization report and included T-Tyler and Carbon Plan Maps because those were I think this was 2023. Those were the only two resources that were really applicable. Since then, we have XPublish tiles, DECGL raster, numeric data layer, ZAR CCM, ZAR GL, and ZAR layer. And for someone who just wants to visualize a data set, a data cube, using ZAR or any other library on the web, this is a really difficult topic to navigate. So I think it would be valuable to provide some guidance on what to use. And so I started out with just an overview of what it takes to dynamically visualize data, because as a backend engineer, this took me a while to understand what actually happens in your web browser. And then what makes DataCube visualization different from just image visualization. And then I think it would be helpful to build this out to understand the similarities and differences between these different approaches, like dynamic tilers, some of the newer ones like XPublish tiles, and all these different renderer layers. I would love it if people submitted comments, in particular, any corrections, anything I got wrong, or additions via just opening an issue, dumping your thoughts. They don't have to be they don't have to be structured at all in the DataCube guide repository. I also think we could have discussions about this on the cloud computing ESIP cluster if Slack is a little bit more familiar to you than GitHub. But in general, thanks for listening. Thank you, Amy, for organizing this. And that's all I have.
Great. Thanks, Max. You do have a few minutes for questions. Does anybody have questions or comments for Max? Yeah, Jared, go ahead.
Yeah, you had 25K as your small chunk size, and that's a pretty big jump from 25 megabytes. Like almost pathologically so. I'm wondering if you tested anything in between, because I would expect that the differences wouldn't be linear. You probably would see something of an exponential curve of inefficiency as you get closer to that pathological small side. Do you have any insight into that?
Yeah, that is it being worst practices. It's like the pathological example is the worst practice using something. And this isn't something I've never seen in the wild. Like I have seen 25 kilobyte chunk sizes. I also do expect it would be some sort of nonlinear relationship between the two. And it would like the reason for using the pathological example is that it would depend, right? Like the point at which you start getting better compression will start to be when you start to have spatial relationships between adjacent cells in your array, and that will depend on what the values are. So for example, if you have a smoothly varying variable versus something that is more sinusoidal or something like that. So I think it would like your instincts are right, and also that is the type of thing that would probably take like a long time and a lot of parameterization to explore. If I were to do it again, I would probably just go to the 16 megabytes. So it's like AWS's optimal chunk size as the comparison, because that is like a pretty okay default, is going with what AWS says is going to perform well on their object storage.
Cool, thanks.
Alexander said that 8 bytes would have been the true pathological chunk size, which, yeah, I have not seen that in the wild, but I guess if you have uncompressed data, you could consider 8 bytes chunk.
Nice. All right. Well, we should move on. Let's go to Joe is next. Joe Kennedy. Thanks, Max.
Okay, so I'm just going to talk about NiceR and NiceR in the cloud in particular, kind of what we're what NASA's doing to make the most expensive, largest Earth observing mission available to the user community. And I'm going to touch quite a bit on actually what the last two speakers talked about at the end. So NISAR is a mission that was launched July 30th. It's a dual band polarimetric SAR system. So it has L band and S band. I'm talking SAR speak here, but the main things to understand about a SAR mission is that it's side looking and active. So that means it's firing microwave radiation down at the Earth. It bounced back. We observe it. The bands matter on how it interacts with the ground surface and vegetation. So NISAR is really cool because it's an L band, which will penetrate vegetation a lot deeper than any other SAR mission that's global right now. And it also has a small S-band system, which is pretty unique, that will cover mostly India, that was developed by the Indian mission. So we get global coverage every 12 days. And the data will be free and open-ish, which I'll talk about in just a sec. This mission is going to be ridiculously huge. It's going to produce 35 petabytes of data a year. It's been downloading data since July, or downlinking data. And this is going to be, I think, a big challenge in the community. The kind of the base product, the SLCs, which the community is familiar with using right now, because that's what the other SAR missions produce, are going to be 30 gigabytes in size for just one scene, one frame, like you kind of see here. And if I was to download that data, that scene and a secondary scene to do INSAR processing, because it's a pair-based processing, and I've downloaded 60 gigabytes of data, the processing workflow, the brand new one developed for this mission, is going to dump 600 gigabytes of data to disk in the process of processing this data. And then I'm going to get my one interferogram out. Most data use and access we see in the SAR community is time series based. So they're not doing this once. They're doing this as the mission goes on every two scenes that they can over time. So these stacks can be hundreds of pairs long later in the mission. What's kind of new for the SAR community with this mission is that there's going to be a lot of products. Sentinel-1, for example, in this graph stopped at level 1. They produced only the SLCs. We're going to have a lot of geocoded data for this mission, which will be new for the SAR community, and there'll be geocoded SLCs, so the users won't have to do that. But there'll also be higher level products like interferograms produced for the science community, offset products to generate velocity maps over Antarctica, and there's a bunch of like focused like science domain products that are going to be produced either by the NISAR mission or some of them by the Opera project. So there's going to be a lot of data, a lot of different products, and a lot of different levels of products. One of the things that I'm most excited about this mission, besides that there's just going to be geocoded products that will be nice, is that the data set's also framed like an optical mission typically is. So there's a geostationary view on the planet. If you know the track and the frame number, you can get a stack of data. It'll nicely align, and I'll hit on that in a little bit. Yeah, and full global coverage. There's also a lot of different ways the data is going to be acquired, different combinations of the polarizations as they're sent out of the microwave radiation and how it's reported when it bounces back. So the data set is going to be complex to work with. There's going to be a lot of the data to work with, and there'll be a lot of variety. So there'll be quite a bit of exploring by the user community. Kind of how that looks is the mission will take an acquisition. It'll be downlinked somewhere. That will be handed over to JPL, which will do the mission processing and generate all these science data products. They'll then hand over the data products to ASF to distribute them. When they're handed over to us, we'll stick them in CMR, the NASA's Common Metadata Repository. That's all of the discovery and search tools. We'll use that primarily. And then we'll also put it in an S3 bucket. And we'll also like send out SNS notifications for people that want to trigger workflows based on new products. So the level 2 product should be available in less than 48 hours. I think we'll see significantly shorter than that, potentially in the less than 12 hours range. And level 3 products are promised in 72 hours. So this will be pretty quick, and the community should be able to respond very quickly to new acquisitions. It's not exactly a cloud bucket, though. It's a cloud bucket inside of the Earth Data Cloud. So it's actually a private bucket, and getting into this bucket and kind of knowing what's in there isn't quite as straightforward as a public bucket is. And Doug Newman's on, I saw, and so I'm going to not get myself in trouble. I'm going to put questions about that to him. But there's a lot of good reasons for this. Primarily, it's the most expensive mission ever for NASA for Earth observing. And this walled garden lets us record user metrics. And Congress, in particular, is very interested in user metrics. So how do you get in and out of this walled garden? And this is kind of where we'll start touching on these chunk protocols and these kind of things. If you're just locally, like I am right now on my laptop, you'll hit the distribution endpoint using your Earth Data login. That'll end up resolving in an Amazon CloudFront URL, and you'll egress it or download it out at using just the normal HTTP protocol. You'll have pretty decent bandwidth, but constrained by your local bandwidth for the most part. And that'll be sort of the same story if you're in the cloud even, but you're not in Amazon's US West 2 region where the data is located. You'll get a bit faster because you'll be in the cloud, but it'll still be just a basic HTTP protocol. If you happen to be in US West 2 in the cloud, all of a sudden these data pipes that you're stuffing the data through get really big. You can have really, really fast access to the data, whether it's HTTP or S3 access. The only way you can get S3 access is by being in the cloud, asking for a time expiring, typically in an hour, access token to get you into the bucket. At that point, you can see what's in the bucket. You can't really see the bucket outside of doing a CMR search. And then you can also use S3 protocols, which is nice because a lot of tools are S3 aware, and you can get a better cycle, and you skip the authentication loop with Earth Data Login. So you can get just a slightly bigger pipe by doing S3 direct access if you're in the cloud. So a really big mission, lots of data products, lots of ancillary data produced by the processing workflows. It's going to mean we're going to see a lot of users be motivated to get into the cloud. So that means there's quite a bit of things that we'll need to do as a DAC, and I'm not going to talk about most of these, but making sure users can find the data is one of the fundamental parts of that. Also access the data performantly. And then there's services that allow the users to offload their computation to the cloud, either for them, like a tool like Harmony that will mosaic or stack or reproject or do these transformations on it, or by putting them in the cloud with a compute environment, something like OpenSARLab or CryoCloud or those kind of things. And then there's how to work with the data trainings. So the most I'll talk about that is that we're trying to develop a community guide to doing all of this in one location. So it's a GitHub repo that publishes the site on GitHub Docs. It's a user guide. It's got everything about the products, how to access the data, how to use the data, some tutorials to work through, some applications you want. And it's sort of targeted very specifically at the data and how to use the data and what you would do with the data, not on the mission history or how the processing system works or any of that kind of stuff. And importantly, we want this to be a community guide, but hopefully the community guide. So we've set it up implicitly to take user community contributions. We would like to reuse and link out to docs that are already available. We don't want to recreate or replace. And we want it to be updated very rapidly. So we're going to take a kind of trunk-based development, ship everything methodology here. So check this out if you get a chance. It is very sparse right now because there's no data that's publicly available. So it's hard to make tutorials and workflows if we can't actually get to the data. So now I'm going to get into the chunking a little bit. NiSAR data is cloud optimized, and I'm always hesitant to say cloud optimized because there's a lot of baggage there, but they're HDF files that the NICER mission based on user feedback in the 2023 community working group meeting that they had. They've coalesced all the metadata out front. They've tweaked it, the page sizes and that kind of stuff, so that it should perform pretty well in a cloud native environment. So tools should be able to take advantage of that. Oops, sorry. Cloud optimized is why I don't like it, is because cloud optimized is always to a spatial pattern, like an actual access pattern. Doesn't matter what you do with the chunks and all of these kind of things, if users are going to aggregate them in the way that's like opposite to how you've set up the chunking. So you can chunk them for time series analysis, and then users will try to grab a bunch of time series and merge that into a big giant mosaic, and that will be really slow because you'll read way too much data. So these granules are chunked in a way that are likely most performant for spatial analysis. We know time series workflows are heavily, or we know that SAR workflows are heavily time series dependent, and as the mission goes on, we'll see a lot more of that usage. So I'm really excited about the opportunity to use these chunks and virtual chunking things to build out these data cubes that at least let you access time series of chunks a lot more performantly, even if the underlying chunks are a bit bigger than I'd prefer. The other thing that's fun with these is it's a deeply nested metadata structure, but they do follow the NetCDF data model and CF conventions, and so you can trick a lot of tools that don't understand the HDF5 files implicitly by just telling them it's a NetCDF file and it'll work. An Xarray data tree in particular, I want to do a shout out. If you're in the Python ecosystem, that's going to be the way you're going to want to look at this data. I talked about this a little bit already. The other thing with cloud optimization is that it also follows catalog optimization, and I don't think it's talked about as much in the community. You're going to be searching for granules primarily, and those granules will come up, and there'll be millions of them. And so you'll have to coalesce those into your access patterns and build things. We can do a lot better if you're interested in time series applications by providing a catalog of the frames, a frame map in particular, and then you only have to find the point once that gives you your stack, and you just open the entire stack. So a lot of this stuff also has to do with how users search and discover the data. So just some quick early results. I got some restricted access to some of the validation data that they're working on. So this is just like one GSLC that Paul let me look at. And it's in an S3 bucket, a private S3 bucket that I have access keys to. So this is sort of like I pulled the Earth data login lever and got the access keys for an hour. And I just wanted to pull a single pixel down and see how long that would take. If I use S3FS, FSpec, it set some basic caching stuff, which is maybe more, as Max and mentioned, than users are expected to do. I can get this using H5Py down to about 59 seconds to go out, get that one pixel from the HDF5 file, and pull it back. That's a long time for a single pixel. If I instead switch my tools around to just S3FS, Xarray, and H5 NetCDF is kind of the stack, and do the same thing, I can get it down to 17 seconds. So I've really only used two, I think, of the most common Python HDF tools here, and I futz with a little bit of the caching and specking. I expect to be able to bring this down significantly once we start talking about kind of chunk manifests and raster stores and some tool optimizations. But even just using kind of a naive approach, kind of the common tools, very little changes can have a pretty significant impact on how I'm able to access the data. And so what I in particular am interested in is in like what things would help the user community. I can make this list for myself and the projects I'm on, but what are people need most in the community is like those tutorials and trainings and that kind of stuff. The most valuable is getting the granular level virtual reference files out there, the most available. should I build the data cubes for frames before I work on transformation services, et cetera, et cetera. And I'm saying I here because this is me gathering feedback to then try and help inform the DAC. But I am not on the mission or the DAC teams. I am a staff scientist for ASF, so I help advise. I don't drive. So yeah, help me help you. Tell me what we need, and I'm hoping that a lot of the stuff that we're going to talk about in this session can make NISAR better. And I think that's it for me. Do I have time for questions?
Unfortunately not. I have lots of questions, but I think technically we should probably move on.
Well, there's time at the end, I think.
Yes, hopefully we'll have a few minutes at the end, and maybe I'll post some questions in the chat too. Yes, let's go on to Dean.
All right, can you hear me all right?
Yep.
All right. You can see my slides in slideshow mode?
Yes.
Cool, thanks. Hi, I'm Dean from PODAC. I've been doing this work with at Armstrong. I'm primarily on the data publication team, but I get to do some cloud optimized work for part of my time. And I wanted to share with you all the way that we have been integrating virtual data sets into PODAC, how we've been creating them and offering them. And so I say virtual data sets, and it's because I'm not as technically advanced as most of you. And so I think what I call virtual data sets, you guys call chunk manifests, like combined chunk manifests. But I think, you guys are all technically better than me to the point where I think you'll know what I mean by virtual data sets. So I just want to talk about our current ecosystem for virtual data sets, and that includes generating the virtual data sets, storing them, storing the virtual data sets, and like linking to them in CMR, and then how we are guiding the users on using them, and then plans for Earth Access integration. So first of all, just the ecosystem overview. We create the combined virtual data sets. We don't do it for the individual granules. It's a combined virtual data set for the entire collection. Currently, we're doing JSON, but the workflow that we're doing should accommodate IceChunk very easily in the future. Then we store that in a public bucket. This is not the same bucket location as the native NetCDF and HDF files that we still ingest. It's a bucket just like devoted to these virtual data sets. And then we found this field in CMR in the UMMC record in the related URLs section, which we can use to point to this bucket location. And from there, anything that does CMR queries like Earth Access or some built-in kind of like functions that we offer the user should make finding the virtual data set very easy from your Jupyter notebooks and Python scripts. We're working exclusively in those. We're interested in other technologies, but that's been the easiest entry point so far. So I'll go into a little bit more detail of each of these points, and that'll take up most of the rest of the talk. So generation of the virtual data sets, just some basics. We create it after ingesting the NetCDF and HDF files, because then we just find them using Earth Access. That's just the way I've been doing it so far. Lowest hanging fruit, generate a single KERChunk JSON for the entire record rather than ones for individual granules. We create 2 copies of the JSON, one for S3 and one for HTTPS access, which we found HTTPS access is also like very doable and very performant. And then we originally generated these virtual data sets using this like homemade Jupyter notebook. We're transitioning to trying to like operationalize this a little bit with cloud resources spun up dynamically, deployed with Terraform. There's a link here to some of the work that our TVA team is doing on that. And here's a cookbook link to the kind of original workflow that we had when I was just using a Jupyter notebook. Some quick metrics: types of collections virtualized, primarily L3, L4 data sets, concatenated along time, with the, each granule having uniform spatial coverage and dimension sizes. We just started trying L2 data sets, concatenated along a dummy time dimension. But those L2 data sets do need to still have uniform, like along track, cross track dimension type stuff. Generation time, when we're using S3 endpoints to access the granules, it's about 30 minutes for an 11 terabyte collection, 15K granules, using pretty modest resources, 20 small VMs. Using the HTTPS endpoints takes a lot longer. Let me see. And then file size, JSONs are about a few hundred megabytes for the size of data sets that we're tackling so far, which are only like 10,000 to 20,000 granules. Ice chunk will be, of course, a lot smaller. Okay, so now where do we store this information of where the virtual data sets live to make it easy to find? And so instead of going through each of these fields in detail, I'll just throw this slide up and you can check it out later. But there is this related URLs field in, or this field within related URLs that we found that actually is called a virtual collection. So this is like the full path to it, and this is kind of the field types and the example inputs that we put. But that goes into the UMMC. And then once we do that, for instance, this is just a snapshot of one of the dataset landing pages for one of the datasets that we've created a virtual dataset for. It's a sea surface temperature dataset. You hit the data access tab, and you're seeing that those virtual collection links are automatically showing there because, right, it's pulling from the UMMC. Okay, so now for user guidance that we provide for using the virtual data sets, we have this PODAC, we have our PODAC cookbook, right? A bunch of tutorials for using our data, and we have a chapter on using virtual data sets. Here's the link up here. In addition to like giving users an introduction into what they are and how to use them, and then links to like some starter notebooks. It has a table of our current offerings for virtual data sets. We've got 10 L3, L4s and 1 L2. And we've cover variables like sea surface temperature, ocean winds, current salinity, water storage, and we have several missions that these variables come from. And then what the actual user experience is like for accessing the virtual data sets and then using it to open. Right, once you find the virtual data set link, which in this case can come from either this, copying the link here on a data set landing page or finding it on the table in the cookbook. Once you have that link, you put it into this, there's this boilerplate function that we offer in one of our starter notebooks. And that nothing needs to be changed there. You just put that in there, and then you get a mapper, and then that mapper goes straight into Xarray, and then you get your data set. I should have displayed more of the output, but this is the sea surface temperature data set. That's like 11 terabytes and 15K files. And then close to the last slide, so future Earth access integration. So you can imagine this function that we use to get the mapper that the user has to copy and paste, that can just go straight into Earth access. And so it'll look something more like, Earth access.get VDS mapper. And instead of needing to know the link, you just do the short name. And then Earth access will do the job of checking if the CMR record for that collection has a virtual data set, and if yes, return the mapper, and if no, return a message like, you got to open this the traditional way. And then whether the virtual data set that Earth Access finds is IceChunk or Kerchunk or something else, we envision having like backend stuff so that Earth Access deals with that, and whatever it returns, this VDS mapper is pretty agnostic to the format, and that just goes straight into Xarray, and the user never needs to know that we've like changed all of our formats. So that's what we envision. The original proof of concept, this is a really outdated PR, but it did work at one point, with older Earth Access versions, just a proof of concept and a demo notebook showing basically this kind of functionality. And then the current effort, I did not update this and I meant to, there's a current effort to more robustly integrate this in Earth Access that was led by Julius. That is, I think he's no longer on that. So some future work, finish Earth Access integration, move to IceChunk. We're really excited about doing that. We're still figuring out how we want to handle forward streaming exactly. And then some challenges to think about. Scaling, I think, is a big one I always think about, because we're using the Kerchunk JSONs right now, and we're watching them get bigger and bigger as we virtualize larger data sets. And then at some point, I'm like, don't worry, IceChunk will save us. It'll scale everything back down by 30x. But then even that's going to start growing and growing and growing at some point, and then we're going to need some new solution. And so I wonder if that's the point where we say we actually don't want to just offer the combined virtual data sets, but we do actually store like the reference files for each individual granule, and then on the fly, like combine and return as the user needs based off of their like temporal and spatial bounds. But that is to be determined. And then how to offer if there's multiple virtual data sets offered for a single collection. I can imagine, especially for L2 data sets, there might be more than one way to go about doing this. So thanks to all these folks. They've made my life way easier because I just have the high level understanding of it. I don't have the details, and these people have all been very instrumental in helping us get stuff up at Podac. So thanks.
That was awesome, Dean. Thanks so much. I love seeing how the virtualized R is actually being, fully integrated into Podac as sort of a first-class data citizen. So thank you for that. Any questions for Dean?
So, Dean, it looks like you've got a full collection level virtual czar.
Yep.
And that is that collection global coverage?
Yes. Yeah, because so we like kind of started with the lowest hanging fruit. So even though like the biggest thing that we've virtualized so far is that sea surface temperature data set that's like 11 terabytes. But each granule has global coverage, and each file itself is like, I don't know, half a gigabyte. So it's like much more manageable than like NICE-R. So yeah, we're working our way up to that. But our goal, at least my goal, was to figure out kind of this ecosystem overview here, and so yeah, for that, I wanted this to not be the hang up point, like figuring out how to like virtualize the like hardest data set ever kind of thing.
Right. Yeah, we should chat more offline, because we, for the Opera project, have virtualized the displacement products globally, and they're broken down into like virtual frames for each of the frames. So like a gridded subsection of the Earth, we built data cubes for. And we also have granule level virtual reference files for each granule. And so we're kind of hitting at the same thing.
I love to talk because that is one of the big next steps is like, and it sounds like you've already figured it out, is these bigger data sets where things are more tiled. So yeah, please let's continue talking.
Yeah. Elizabeth, maybe just quickly, if your question's quick, and then we should move on.
Yes, question for Dean. It's kind of following up on the chat. Do you have the questions about pipelines that I put in the chat? Do you have the actual code that you were using to process like those 11 terabytes that you did in 30 minutes? You don't have to answer here, but maybe you can throw in the chat if you have that in a repo or something.
Yeah, here it's in this slide here. I mean, this is
perfect.
the original, like fully public, like Podak cookbook version.
Nice.
It could have been, because this is kind of gets just like customized and updated for every new virtual data set that we do. So if you have any questions, reach out to me, and I might even have a more updated notebook that's somewhere on my GitHub, but like not publicly available. But for now, I'll just stick this one in the chat, and then it's also in the slides.
And yeah, sorry, Dean, we should probably keep going so we have time for everybody. Of course,
sure.
We're going to run out of time, even though I buffered extra. But so yeah, Owen, are you ready?
Yeah, let me share my screen and put it on presenter mode. Hopefully you can see this. If you can't, please let me know. But yeah, I'm Owen Littlejohns. I'm the system architect on the NASA EED3 transformation train. And essentially that means I spend a lot of time thinking about what comes between an end user's request for specific bits of data or data in a specific format and actually what's natively hosted in the archive. And so today, I'm going to talk a little bit to start with about how we might achieve the sort of transformation we need to get from A to B there, before talking about how virtual data sets can enable either things on the sort of single file scale, kind of like what we were just hearing from Dean towards the end of his talk there, but then also that bigger picture of having whole collection virtual data sets, which I think is very powerful, but feels like it's sort of cranking it up to 11 and taking that next bigger step. And then how we could maybe roll this out across the enterprise, also taking into account what we just heard in the last sort of 10, 15 minutes. So currently right now, there are a lot of different services that exist out there. I'm not trying to take credit for these things that are linked in that top bullet point. Lots of different groups have worked on these things, but they're all doing some awesome things to transform data for the end user. Even though both the services and the data are in the cloud, quite a lot of the time, we're not really taking advantage of that. Some do, but yeah, I'm going to dig into some details in a sec now. So probably the most common way that data are transformed, a user request comes in on the left there, it hits some kind of API, and then it gets to the service. And the service will make use of two pretty core pieces of information. There'll be some kind of metadata catalog telling you where the files you care about or the objects in S3 are. And then there will be the objects or files themselves. And the big sort of flashy thing in the middle of the slide there in sort of red letters, quite often what's happening is that transformation service is downloading that native file from wherever it is in, say, S3 and moving it over to some sort of storage that is local to the compute doing the transformation. And that's whole scale, moving whole files often, and that's hundreds of megabytes, could be gigabytes, and that's not really very performant. An alternative, and this is something that's available today, is something like Giovanni in the cloud. And this gets us closer to more sort of cloud-centric models of doing data analysis. Again, a request comes in, it hits Giovanni, and Giovanni has a metadata store as a JSON object that says, hey, for this measurement of interest, this science variable, you care about this ZAR store. And then they have these duplicated stores of data, which are in a ZAR format for each variable that's been considered high enough value to duplicate the data. And so it can do this performant access against an actual ZAR store and pull only the bytes over that really the user needs. So it is much more efficient, but it has that sort of duplicated data. A third option, and again, this is something that happens today, we have Harmony, which is a workflow orchestration engine, and behind that we have lots of different transformation services. One of them is the Harmony OpenDAP subsetter, HOS. So again, request comes in, it hits HOS. HOS is using information from CMR, the Common Metadata Repository, to find the files it cares about. And then it's doing something a little different to other services. It's making a request to OpenDAP for the dataset metadata response document, the DMR, which isn't quite a chunk manifest. It doesn't actually have any chunk information, but it does have all the sort of structural information for, where the variables are in respect to sort of the netcdf4 layout, what the metadata attributes are, and how variables relate to one another. And so it uses that DMR document to build the request it needs to make to OpenDAP to retrieve only the bits of the native data file that it really wants. So it's doing that sort of more tailored retrieval of data, but it is using an extra service to do so. So sort of comparing those three things side by side, sort of just looking at the emojis for a second there, it's a mixed bag. Essentially, nothing's perfect. Each have sort of positives and negatives, but the big sort of showstoppers perhaps are either downloading whole files, having to duplicate data, or having to use something additional to get the data without having to get the whole file. And just to note, like I'm saying about having to go through OpenDAP, there's nothing specifically bad about OpenDAP. It's just adding that extra step that is the bit that we'd like to avoid. So thinking about this leads into the prototyping work that's going on in the transformation train right now. And it's sort of letting me answer a question that I've been asking for a little while. What if we had something like HOS, but we didn't need to go through OpenDAP? So I get to have some fun and games playing around and trying to make this work, which is I quite like, really. Having just heard from Dean and others sort of just now about these sort of whole collection virtual data sets, there's maybe a valid question as to if we should bother with sort of single file transformations using virtual data stores. And I think the answer is yes. Firstly, it's an easier step to take in the short term. If something is already configured to have support with OpenDAP, we can make use of the DMR++ document, the chunk manifest, to enable this. So we already have the ingredients we need, but also we can start maybe transitioning over some existing sort of per file transformation services so that they're using this virtual dataset access. And that's perhaps an easier step to take, particularly for things that are already using things like Xarray, than perhaps having to build out a whole aggregated chunk manifest and work out how to maintain that and where to put it in CMR. So it feels like a more sort of digestible step to make. And also it has the benefit of showing that within something like Harmony in the sort of bigger ESDIS ecosystem, we can use this software stack effectively, and we can see some of those performance gains that would be nice from not having to move gigabytes around. So to do that, I need to choose a good collection. Most of the criteria on this slide are essentially what makes my life easier. And in fact, it's quite funny because essentially what I ended up doing was narrowing down onto a collection that Podac, I think, have already created, a whole collection virtual chunk manifest for. The other point in here, though, is the large files. So aside from being able to make it easy, make it more about proving the technology stack rather than dealing with data quirks, also by choosing a large file, we can show some of those performance benefits. And then just as a visual for one of the collections that looks really promising, this is a sea surface temperature product from Podac. And you can see from the figure generated by Panoply here, it's gorgeous data. Each pixel is 1/100th of a degree on both sides. So that means there are hundreds of millions of pixels in each file. And that adds up to, I think we just heard something like 500 megabytes, sorry. So that's a lot of data to be moving around. How am I hoping to do this? I've actually started work on this recently, and I'm trying to sort of work smart, not work hard. I was really lucky back in August to go to the ISAT2 Hack Week, and during that got to work with folks like Luis and co on some Earth access changes. There's a file linked on this slide, the DMRPP zar.py. And that essentially has the workflow that I'm looking to bundle up inside a Harmony service. So what that means is finding the file we care about, pulling the DMR++ file, passing that with virtualizar, and then generating a chunk manifest, and reading that with Xarray. And then once it's in Xarray via that mechanism, you can do the slicing and dicing that you might want to do for, say, spatial subsetting, and then materialize the output as an etcdf4 file at the end. So really trying hard to just reuse what's already out there, use some of the experience gained from that Hack Week. And so when trying to do that, it's going to look very similar. This is the same diagram, but for that single file virtual data store model. This looks very much like HOS and the diagram I showed for that. So request comes in, hits the prototype, and it's retrieving metadata, in this case from the Common Metadata Repository, CMR. It's using that to locate the DMR++ file for the single file, pulling that over, and then using that, as I described, to essentially create a virtual data store. And then it can access the bytes it wants without having to go through OpenDAP. So this gets us quite a way towards where we want to be. All these positive check marks here. We're only getting the data we want. We're not duplicating data. We do have to have a DMR++ file, though. A lot of the stuff in the ESDIS archive, particularly gridded data, does already have the DMR++ generated, and there's work ongoing to generate even more for data, for example, for the JESDISC. We don't have to use an external service, so we get to cut out that extra step in the chain, and we get to start using the sort of technology stack we've been hearing quite a bit about over the last few talks. We've got things like Xarray and Virtualizar and Kachunk, and so part of the benefit of that is there's all these smart people that have been working on this for a few years, and we don't have to start from scratch. We can use the sort of community strength there to really try and just, I guess, plug in sort of almost boilerplate code to just make it work in a new environment. And that also means that we're not having to maintain custom code of our own, so it makes our own maintenance easier and simpler. One thing we haven't gotten to, though, is this is only single file operations. So the next step is to move towards some of the things we were hearing from Dean just now with that whole collection virtual data store. And so that's going to be the next step after I've finished off the prototyping that I was just talking about. I don't need to maybe go into too much detail because we've just heard a lot about this already, but in my mind, at least, this is sort of adding a layer between the native archive and then sort of how users perceive it to enable, different access patterns. I think Joe kind of talked to that as well pretty well. Maybe people want time series or time averaged areas, all sorts of things. I think the Giovanni team, in fact, has a lot of good use cases that they've been able to enable with actual ZAR stores that we can perhaps try to recreate. To do this, we basically need to do what Dean just said. So we need to have this aggregated chunk manifest. We need to save that somewhere, and we need to put it somewhere that people can find the link to it. And CMR, I think, is the obvious candidate there. And so what this will look like, again, I think this is the last time you're going to see this diagram, very similar to the previous one, except that one CMR is queried. What's being retrieved is, instead of a single chunk manifest for one file, it's the aggregated chunk manifest for the whole collection. And then that's being used to open an Xarray object and then access everything like a virtual data store, and then only get those bytes that we care about. But it can happen regardless of whether some of the data are originally in one file and some are in another. We don't really care about sort of artifacts of how the data were gathered and the products generated. We care about like how to get the user what they want and sort of get past some of those boundaries, which is awesome and hopefully makes life easier for people. To do this, again, as Dean said, it's kind of convenient I came after him. We do need to represent this in CMR. On the right there, that JSON blob is essentially what Dean showed for what PODAC is doing. On the left, please don't strain your eyes sort of looking at it in detail or anything, but this is an alternative. So Giovanni in the cloud has ZAR stores per variable, as I mentioned. And so in the UMM var record, instead of UMMC, they've been producing content that looks like this. I don't have strong opinions either way. I think that the important takeaway from this slide is we have a bunch of folks working on making virtual data stores available. We should probably just be talking to each other and do it in a consistent way across the enterprise. Maybe the metadata stewardship team on the search and discovery train might be a good venue for sort of having those discussions. But yeah, let's do it the same way, basically. And then how far does a whole collection virtual data store get us? Well, all of the previous points, but then also enabling these whole collection operations and things that might be grabbing data from more than one original netcdf4 file. So what do we need to do to make this happen at scale? I don't think this is difficult. We just basically need to do, again, what Dean said. We need to be making these chunk manifests. We need to be putting links to them in CMR. And then at that point, we have something that's accessible both to our internal tools for transformation, but then also end users can start using these virtual data stores to do all sorts of things like these long duration time series, but probably things we haven't even thought of yet. And I think we have all the pieces that we could be doing this right now. I mean, Podac are already publishing these things. They're out there in the dataset landing pages for people to find. So this isn't a question of, hey, what extra things do we need to add into our sort of overall ecosystem of software? It's, how much do we roll this out at scale? There are some caveats and nuances with all of these things. So to be sort of fairly transparent, some things are still being worked on. One potential avenue of things to consider is for active missions, more data come in as more data are gathered. And so we need to be able to keep the aggregated chunk manifests up to date by appending to them when new data are available. Sometimes it's difficult to aggregate for different data products. I mentioned before that I essentially chose something very easy because, among other things, it's easy to stack along existing dimensions within the individual files. Sort of shout out to Max Jones as well. Hierarchical data has been a little bit tricky to work with. I think Joe mentioned data tree, but getting everything to work nicely with a virtual data set, but in a hierarchical tree format, it's been a little tricky. And Max Jones has a PR open right now that tries to make that all work a bit more nicely. And then also, every now and again, we've heard sort of level 2 data in these conversations and how that's more tricky because per file, the chunk shapes and sizes might vary. So that does make things a little more difficult. So wrap things up. Virtual data stores are awesome, as we've heard today. I think that they're valuable both at that whole collection level, but also if we're trying to do transformations on a single file. I think not moving whole hundreds of megabytes or gigabytes around is going to save us, performance-wise. But then, turning it up to 11, enabling new use cases, those whole collection virtual stores are even better. We have a lot of the ingredients we need. In fact, I think we have all the ingredients we need, but there are going to be quirks to work through. But yeah, let's get these aggregated chunk manifests out there, but making sure we're doing it consistently across the enterprise. I guess one last shout out. There's a co-working session that Amy has started recently. All things virtual stores, trying to sort of work through some of the things I listed as perhaps issues that we need to just tighten up and try and solve together. So I guess if folks are interested, Amy's probably the person to reach out to join those co-working sessions. That's what I got. Thanks very much.
Thanks, Owen. Yeah, I love your really though slide was a really great summary of all the work that we have to do in this area. Before I pass it off to our last quick presenter, Miguel, who's going to do a wrap up of the chunk manifest, I want to make sure that people know where to go next. If you want to continue the conversation, just putting in the Slack channel the join Slack link. So if you're not already on Slack and you want to continue, or if you are in Slack, please join the Cloud Computing Cluster where we will be continuing some of these conversations. So with that, I'm going to pass it off to Miguel to close us out with a report out from yesterday's session on chunk manifests.
Yeah, sure. Thank you. Let's see. Share my screen. Try to be brief. All right. I'm hoping you're seeing my slide. Is that correct?
Yep.
Okay, good. Yeah. So this is a bit of a report from yesterday's session. I will really brief. This is just essentially 4 slides. We had a great session yesterday, essentially about chunk manifests. And we had like close to 35 people. We talked about close to 13 different chunk manifest approaches. I call them chunk manifests, but some of them, for example, HDF, they have their own like internal representation of the chunk manifest. Similarly, Virtualizar, you can think of it as an in-memories, but we talked about a variety of different approaches that people are using. Hidefix, which, for example, is based on the MRPP, but it's on Rust. That's also pretty interesting. Parquet, Zar, of course, and then Cloud, for example, all of these other formats. I put a little figure here of the MRPP. We had a bit of a consensus yesterday of like how many of these people were familiar with, and we had a lot of Kerchunk. We heard a lot of Kerchunk, Zar, Virtualizar, and the MRPP, which were mostly the most popular ones. Which was it was not surprised given that this is ESIP. And so one of the sessions for the session today, we had this kind of activity, breakout groups, and kind of like try to understand like what is a chunk manifest and why is it that a standard is needed. And so there were a lot of input for a lot of great people from all across the spectrum of organizations. Also different backgrounds, like software engineers, scientists from NSF, from NASA, from different organizations as well. I think we kind of came up with like a bit of a collection of definitions. So we discussed them, but broadly, chunk manifest is kind of like a portable, quote unquote, human readable, perhaps, description of a data set broken into chunks and how to retrieve them efficiently. We heard a lot about table of contents of maps, array level concepts. I really like a lot. A colleague had said a Rosetta Stone, which was a standard format agnostic Rosetta Stone, kind of a type of document that enables this interoperability between different APIs and the such. And so, again, I'm trying to go really quickly. And then in terms of like why is it that it's a content metadata standard is needed, it's just essentially broadly to make it easier to build clients and tools that work consistently across dataset and formats, improve interoperability, scalability, and computational efficiency across different libraries. It kind of reduces the need to duplicate efforts or replicate representation by providing a common lightweight Rosetta Stone kind of approach that supports discoverability, standardized subsetting of large data sets, or potentially small data sets, and enable a faster assembly of multi-source data sets, and kind of while preserving the provenance of the original files. And so it was kind of like a very interesting, and this is an evolving work that we're all like trying to kind of push forward to have like this like kind of regular, potentially some sort of effort in the next couple of months. And the second part of the session, we kind of like started to focus and divide into groups in terms of like, okay, we are familiar with a couple of these chunk manifests. What if we start looking into like, what is it? Where are the intersections between them? Where do they overlap? I think that's one of the biggest questions that people have, like, how do these overlap? How do they don't overlap? Or perhaps we don't understand they do overlap, but we think they don't. And so we had kind of like a working breakout rooms in terms of like, okay, we know a little bit about, for example, Virtualizar or Kerchunk. How does it compare, for example, for this group index that I wasn't familiar with, that it's supported by the TDS, the Threads data server, and then that was like really interesting. How they both represent byte ranges and support numcodecs, but where do they differ? We had DMR++ and ZAR. There's a couple of open-ended questions, and some of them because there's still no consensus of what these all, like, how do they really overlap or they don't. We had 6 different ones. We talked about Parquet as well. I just moved a different slide. But it seemed to be that there was a lot of common knowledge or interest in both Virtualizar, Kerchunk, ZAR, and DMR++. So we had a lot of repeated efforts in terms of trying to understand. And again, some kind of questions, and some of them have answers that we didn't really have enough time to discuss. I went really fast. There was a lot of interest, and I think there's a lot of moving interest. This is my last slide, by the way. And so kind of like at the end point of this session from yesterday wasn't about coming up with a solution to the full answer, but rather to build the momentum and maybe hopefully to continue the momentum. And this is where we started talking about potentially some sort of subgroup within the cloud cluster that Amy is in charge of. And we have some interest from a lot of folks in terms of like, okay, maybe we should continue this conversation and work towards a standardized content metadata standard for this chunk manifest. We don't want to replicate like what's already been done, but we really want to make sure of like it's a consistent interoperable document that can be used across the spectrum of APIs. And so with that, that's my last slide. So thank you for that. Let's see.
Thanks, Miguel. And thanks everybody who is able to stay over a little bit. Again, join us on Slack. I'm excited to support the Chunk Manifest Specification Initiative with the Cloud Computing Cluster. So if you join us on Slack, we will follow up there with a continuation of the discussion, probably in one of our recurring Cloud Computing Cluster meetings. There are a couple another great sessions coming up. So I have the Bridging the Cloud Divide Part 2, which is starting in an hour, I believe. And then there's also Enabling Data Standards, I believe, is another simultaneous session concurrently running. And so unfortunately can't be in two places at once, but either of those would be great sessions to join after this. So with that, I want to give everybody a nice break before the next session. So thanks y'all for joining, and looking forward to seeing you again soon. Bye.